And
Just
okay.
start recording.
I'm Tzu-Hsuan Huang, a Ph.D. student from National Tsinghua University. And I think it's very honored to share some knowledge of content error correction and present our work. So my topic is decoder for content error correction codes from the perspective of classical error correction code. Because as a EE student, my master research direction is classical error correction. So I think this talk is aimed at researchers or students like me who are newcomers to the quantum world, but have a certain interest in it. So let's get started. So this is my outline. I will first introduce classical error correction and quantum error correction. Then I will focus on the belief propagation decoder and present our work. And finally, I will mention some decoder issues. So first, what is error correction? So the whole communication system is like this figure. And before transmitting the message, channel encoder will add the redundant bits to protect the original message. Then the output we call the code word. Then after passing through the noisy channel, the channel decoder will recover the received word to the code word and output the original message. So that is the classical error correction. So what is the difference with or without error correction? So suppose now we know the performance of an uncoded system. Then by using error correction, the curve moves to the left. So now the system in a more noisy environment, say that X2, can still maintain the same error rate. Alternatively, in the same environment, for example, X2, the code system can provide a lower error rate. So I will prepare some image. Let's say this image, noise caused the photo to obscure. So we don't know what are they doing. While using error correction, we can recover it. So now, oh, I see, they are playing switch. So that is how error correction does. So a common error correction code is using linear block code. And NK linear block code is defined if only if it is 2 to the power of k code words form a k-dimensional subspace of the vector space phi. And phi is n tuples of a Galois field 2. So in this talk, we only consider elements in binary. Then for a binary linear block code, we can there exists k linearly independent codewords such that every codeword is a linear combination of these a k linear independent codeword offset basis. So we can form this basis as a generator metric. So for any message U, we can obtain the codeword by multiplying to the generator metric G. But often we will use the parity check metric H, which means that the codeword space is the null space of this parity check metric. And every codeword times H is 0. And further, we know that the message times G is a codeword. So we can see the relationship between G and H. Thus, the code can be characterized by H. So now suppose we obtain a received word Y, which contains the code word and an arrow. then by multiplying to the h, we can obtain the s, which we call the s the syndrome of this arrow. So now I will introduce the low density parity check codes, or say LDPC codes. It is proposed by Gallagher, and it's a class of linear block codes that can provide near capacity performance on many channels. And a graphical representation is proposed by Tanner, now called the Tanner graph, which is useful for decoding algorithm, as we will see later. And with the work of Mackay and Ruby, a research on LDPC code revived in the mid-1990s. And LDPC code's parity check metric has a low density of 1. And we say a regular LDPC code is a linear block code whose H has a constant column weight and constant row weight. Otherwise, it is an irregular LDPC code. And last, an important constraint called row column constraint, or say RC constraint, which says that no two rows or two columns have more than one position in common that contains a non-zero element. So let's see an example. Given a 10-5 code with parity check metric as follows. So we can see the row weight is 4 and the column weight is 2. Then we can transform this H to the Tanner graph, like this one. So a Tanner graph is a bipartite graph whose nodes separate into two types, and edge connecting only nodes of different types. So the two types in a Tanner graph are the variable node, the circle, this circle calls variable nodes, and the check node. And check node I is connected to the variable node J whenever element in H is 1. So in this case, there are 5 check nodes in a Tanner graph, 1 for each check equation or row of H. And there are 10 variable nodes, 1 for each code bit or column of H. So we can see that the column weight, in other words, is the variable node degree, and the row weight is the check node degree. And the sequence of H forms a closed path in a Tanner graph is called a cycle. And at high density, many short cycles will exist, which is harmful to the iterative decoder. And the length of a cycle is equal to the number of edges in the cycle. So for example, the dark line formed here in this example forms a cycle 6, because you can count the edge 1, 2, 3, 4, 5, 6, then go back to the variable node 0. And RC constraint eliminates length for cycles. But for quantum codes, it's very different. So we will see later. So let's look at the quantum error correction. So error causes qubit state to another point on the block sphere. So the error can be arbitrary. So can map the original state to another state on the block sphere. So it's continuous. So the problem is, how can we correct a continuous error? So fortunately, it can be represented by Pauli matrix or set basis. That means correct set of those discrete errors is sufficient to correct arbitrary error. So as we all know, for a single qubit, the polybases contain I, X, Y, Z. So for example, X can be viewed as a bit flip operator, which calls 0 state to 1 state. And Z is a phase flip, and Y will cause both speed and phase flip. Then together with the multiplicative factors, we can form a polygroup. And consider n-qubit system. The n-fold polygroup is a polygroup tensor product n times. So now we can model the noisy channel that cause errors. One way is to view bit flip and phase flip channel as two independent channels. And for each channel, there is a flip with probability P and no error with probability 1 minus P. Or we can also use the depolarizing channel. So each error occurs with equal probability P3 and no error with probability 1 minus P. But of course, there are many channels modeled for different occasions. For example, the phenomenological noise model, often for fault-tolerance computing, will consider the gate errors, syndrome errors, and so on. So the difference between quantum and classical error correction code is that, first, not like a classical repetition code, there is no cloning theorem for quantum mechanics. So what can we do? We expand the original Hilbert space to a higher dimension Hilbert space by entangling with other qubits. So for example, the original state has 2 dimensions. Then we expand to 4-dimensional Hilbert space. But the core space is still 2 dimensions. And second, for quantum codes, there is phase error, which is different from the classical counterpart. So what can we do? We can use, sorry. Okay, so we can use the Handmark gate or operator to change the basis. So the phase flip is like a bit flip for a new basis. Last, we can't measure the data qubit state. Otherwise, sorry. Okay. So we can't measure the data qubit state. Otherwise, the state will collapse. So what can we do? We obtain the syndrome of error by measuring the ancillary qubits. And those decoders are called syndrome-based decoder. So now let's look at a general scheme. So first, K qubits original state site is entangled with n minus K qubits and to the encoder. Then the output n qubit states will go through the channel. And at the receiver, we will prepare n minus K ancillary qubits to extract the information by using a control operator. Then measuring those auxiliary qubits, we obtain the syndrome. We do the measuring and we obtain the syndrome. Then the syndrome will feed into the classical decoder to obtain a possible error candidate. Then we recover the original state by the possible error candidate. So now we consider the stabilizer formalism, which I think is very important for students of classical error correction who want to know quantum error correction. So an NKD stabilizer cause is defined by its stabilizer group S, and all the elements commute mutually. And a stabilizer group can be characterized by n minus k generators, and each generator belongs to n tuple poly group. So now we can define a coord. A coord commute with all the elements in stabilizer group and is defined by like this. So in other words, stabilizer group fix coord space. So now you can see that n minus k generator, it's just like the parity check equation for the classical code. And let's look at the arrow, which belongs to the n-fold polygroup. It can be divided into three types. First, detected arrow, which anti-commute with an element in S. So we can verify only using n minus k generators, and each generator is corresponding to a syndrome bit. So if an arrow anti-commute with a generator, then the syndrome bits will be 1, otherwise will be 0. So then we can observe the syndrome B1, then we know where the error is. Then second, error that belongs to the centralizer of S, but not in S, we call the undetected error. That's because these kinds of error cause the original code to move to another code. So the syndrome will still be 0, and we cannot detect it. There is a degenerate error, which is very unique for quantum codes. So in a mathematical way, say that degenerate error is the error equivalent up to the stabilizer group. So for these kinds of errors, we can use the same recovery to decode both E and E prime. So for the optimal decoder, there is no need to distinguish them. But as we can see later, that this kind of degenerate errors is harmful for the suboptimal decoder like BP. Now I will introduce the poly to binary isomorphism. So polybasis can be represented by the binary factor. So the stabilizer can also be represented as a two binary parity check matrix, Hz and Hx. And the commute relation becomes twist product or say symplectic product. But note that the commute relation also results in an even overlap in the matrix. So which causes the cycle in the Tanner graph. And and those cycles are very harmful for such an iterative decoder like BP. So likewise, the B-flip and phase flip channel models can be analogized to two binary symmetric channel. So from now on, a quantum error correction problem becomes a classical problem. And because of the binary isomorphism, it's natural to transform classical codes into quantum codes. So there are quantum LDPC codes, quantum BCH codes, quantum polar codes, and so on. And in addition, there are many different stabilizer codes, such as CSS code, and bicycle code, general bicycle code. And there are also some topological codes, for example, the popular service code or Tori code. And recently, the Balance product code was proposed. And last, the hypergraph product code is also very popular. So in this talk, I will briefly introduce the hypergraph product code because our work is focusing on it. So hypergraph product code is also a class of CSS code. So the parity check matrix follows this form. There are two classical matrices on diagonal axis, and they satisfy the relation. And each metric is obtained by the tensor product or say chronicle product of the base metric H1 and the identity. So if a base metric H1 is a full rank repetition code, and then H forms a surface code. So just like this figure, so this is H1. So it's the parity check metric of a full rank repetition code. And if the basic metric is a full rank closed loop repetition code, H forms a toric code, like this figure. So it's a closed loop repetition code. Then if H1 is a random code, H forms a quantum LDPC code. So now I will introduce an interactive decoder called belief propagation, or say BP. So BP performs inference on graphs and is popular iterative decoder for LTPC codes because it is fast and has low complexity. So under the assumption that each variable node is independent, a BP approximates the original problem to find the minimum weight error to the element-wise optimal problem. So in practice, we usually compute the message using a log likelihood ratio to maintain a numerical stability. And the initial value log likelihood ratio LLR value assigned for each variable node depends on the channel model and the received signal value. So for example, for Gaussian noise channel, the initial LLR value is 2 times the received value divided by the variance. So then after the initialization, iteration begins. Message pass from the variable node to the neighboring check node. And we record the value to the queue. Then the check node compute the message by this equation and pass to the variable node. We record as R. And now we can compute the new LLR value for each variable node. And in the next iteration, we get the new Q value by subtracting the previous R value from the new LLR value. So as you can see, the update of the check node to variable node is the most complicated. The phi function will contain a hyperbolic tangent function. So to further reduce the complexity, the mean sum decoder is proposed, which only passes the minimum value of Q. And to compensate for the performance loss, a factor depends on the iteration is also introduced. But in practice, we will just set beta, the factor, to a fixed constant. So for quantum codes, the syndrome-based BP is used. And the check node to variable node update will take the syndrome into account. And other will follow the mean sum algorithm. But since we can't measure the data state itself, we can only initial each variable node with an equal LLR value, which only depends on the channel probability. So the BP will suffer from a performance loss due to the lack of different information on variable nodes. And in addition, degenerate errors will result in many errors with the same weight and the same syndrome. So BP cannot decide which one is the solution and fail to converge. Last, there are many short cycles in the telegraph, and which violates the assumption of BP, which is the independency of each variable node. So another way is proposed is using BP to yield a different log likelihood ratio then as an input to other decoder. This method is called a BP plus order statistic decoder, BP plus OSD. So after BP, we obtain different log likelihood ratio for each variable node, and we choose a rank H most unreliable nodes, say U. We omit the value of those unreliable nodes and assign the new value by multiplying the syndrome with the inverse metric of HU. And where HU is the corresponding submetric of the reorder H. So OSD has a parameter lambda. If the lambda equals to 0, we call OSD 0. It means that the decoder will suppose there is no error in the remaining, I think is n minus rank H in the remaining nodes. Okay. And if the lambda is larger than 0, the decoder will test the number of lambda combinations from these remaining nodes and compare them to order 0 to find the lowest weight candidate. So you can see from this figure, the performance can be improved significantly by OSD. So the line upper is by BP, and the solid line is by BP plus OSD. So the performance gain is very large. But since the OSD requires sorting, metric inversion, and a weighted greedy search, the complexity is much higher than BP. So now I will present our work on BP decoder. So since topological codes are highly degenerate, the BP will suffer from performance degradation. So our work is to improve BP decoder on surface code and toric codes such as such topological codes. So first we analyze the code structure of toric code and surface code. And we've shown that a no-weight arrow has the identical syndrome. And at least one type of weight-2 arrow has the identical syndrome. So for example, given a weight-2 arrows with index J and J plus 1, and which also belongs to the same block column in in S2. So for example, this black column and this black column. And we can find another way-to arrow with index belongs to different black column in S1. So we can find another way-to arrow with the index in S1, and both arrows have the same syndrome. So the BP cannot distinguish. And for larger weights, because larger weights can be obtained by combining a way 1 arrow pattern and way 2 arrow pattern, we omit the analysis. So second, we observe from BP. I will use an example. Suppose now we have the measure syndrome, 2, 3 to the 55. So for this syndrome, BP cannot converge. And we observe that most of the time at the 0 iteration, the hard decision output will include all the indistinguishable arrow patterns. So the corresponding syndrome is canceled. So we use the red to mark those indistinguishable patterns, while blue indicates distinguishable. So during the iteration, we can also observe that the estimate syndrome might be close to the measured real syndrome. For example, 23rd iteration and 24 and 26 iteration are close to the measure syndrome. So there are two cores of our algorithm. One, we want to decode from the syndrome that is closest to the measured syndrome. And second, from the previous analysis, we know that the BP is much easier to converge if the error weight is lower. So the lower error weight possibly corresponds to a lower syndrome weight. So we want to decode using the lower weight syndrome. So we introduce a new decoding path from BP using the syndrome residual. So to identify the closest syndrome, we will use the estimate syndrome at the 0 iteration as the benchmark. So we propose two criteria. First, the chosen estimate syndrome should be closer to the real syndrome than the benchmark. Second, to give the effectiveness of syndrome pruning to obtain the syndrome residual, the index of the estimate syndrome should be in the real syndrome. So here is the schematic diagram of our algorithm. So this is the original BP. And we introduce a branch by using a syndrome residual. So following our criteria, the estimate syndrome, for example, at 123rd iteration, will satisfy both criteria. Then we doing the syndrome pruning. The remaining residual syndrome has index 2 and 3, which corresponding to a unique weight 1 error, V3, and a decoder succeed. So for the considered toric code and service code, the proposed BP, a branch assist BP, can reduce the number of unsolvable way 2 and way 3 errors around 50%. And we call our branch assist BP as BBP algorithm. Note that since we add a new branch, so there are two iteration items, and both maximize set as a code length n. So at first glance, it seems that our, our proposed decoder can improve the BP only because we use more iteration. But from this figure, we can see that the proposed algorithm does provide a better gain at the same average number of iterations. Then we further improve our branch assist BP to deal with loss errors that BBP cannot solve. We propose a LLR side flipping process to provide diversity in the syndrome residual. So the steps are, after computing the estimate syndrome at a case iteration in the main BP, we record the different index at U by comparing the estimate and real syndrome. Then we find the variable based on U and flip the sign of its LLR. Here is the schematic diagram of the whole algorithm. So the side flip process will change the LLR and feed to the next iteration. So it might enhance the chance for the syndrome to enter the branch. So we propose three different selection strategies. So first is global selection. We search from all the variable nodes, neighboring all the mismatch check nodes, and we select the variable node which has the most neighboring check node in U. And second, we propose reliability-based selection, which is that we randomly select a check node from U, and we select the variable node with the least reliability neighboring this check node. Then last, we randomly select a check node in U and randomly select neighboring variable node. So it is shown that different selection strategies will affect the performance. For Toricode, the global and reliability base provide better performance. And we also list the reduction ratio for unsolvable way 2 and 3 errors by combining the side flip process. So you can see the reduction ratio is about 90%. But since the process involves random selection, it cannot guarantee success each time. And interestingly, the SF process can not only provide diversity for the branch, but also speed up the convergence. For example, compared to a BBP, to obtain the same error rate, BSF BP needs less iteration. And for the Toricode, the circle is the Toricode, the improvement is significant. So now I will show the performance. So for Toricode and surface code, our BSF BP, this curve, can outperform BP about 2 orders of magnitude. For the Toricode, unfortunately, it cannot pass the OSD method, this one and this one. But for surface code, it surpasses both OSD 0 and higher OSD. So in paper 25, the lambda is set to 60. And in addition, BSF BP can provide a significant gain if appending to the OSD. So we also found that the SF process can be used for decoding quantum LDPC codes. And to further speed up the convergence, we propose a multi-qubit side-flip process. So the steps are, after selecting the variable node in SF, we discuss the corresponding check node in U. Then we select another variable node based on the remaining U prime, and we repeat until U prime is empty. So we can see the performance by using single qubit SF, which can be close to the OSD3 or OSD5, depending on the code length. So note that the lower the density, the lower the correlation between each variable node. And since using multi-qubit SF, we change multiple nodes at once. But those nodes might be correlated if the parity check matrix has a high density. So we can see for the low density codes, the performance by using multi-qubits is improved. And it can even outperform the performance by using a single version. So overall, the complexity for OSD is n to the power of 3 plus n times 2 to the power of lambda. And our proposed algorithm has an additional complexity for each iteration, which is average variable node degree times variable degree times average check node degree. So as you can see, the additional term is much smaller than n. So last, I will briefly show some decoder issues that I haven't mentioned before. So fault-tolerant computing. So in practice, quantum gates are subject to errors which should be accounted for, and measurement is also subject to error. So multiple rounds of stabilizer or other methods should be performed. And apparently, once considering those errors, the performance will be worse. So new decoders or even new codes, like recently I noticed that there are single shot codes, and the decoder is using BP plus OSD are proposed. Second is the threshold. So the theory says that below a certain threshold, logical error rate can be arbitrarily low. For simulation, it refers to the physical error rate corresponding to the cross point using codes with different distance. So as this figure, so there are different distance is the surface code. So by using the minimal wave perfect matching, it will yield a threshold around 10%. However, not all decoders or codes provide the threshold. For example, BP for quantum LDPC codes has threshold around 6.5%, while no threshold for surface code. So improve BP or other decoders to have the threshold for topological code is also important. Finally, the latency. So due to the qubit decoherence, the timing constraint for the decoder is within hundreds of nanoseconds to several microseconds. And even implementing BP plus OSD0 will fail to achieve the constraint, while BP can accomplish the timing requirement. So although OSD has the best performance to date, we should think about improving BP or propose other lower complexity decoder. And in fact, some theoretical decoder have been proposed. So I think it's interesting to implement different decoders to verify their latency with VLSI technology today. So that's the end of my talk, and thank you.